Assalamualaikum and salam sejahtera. My name is Nur Fatini Nabihah Binti Yahya from MT4. Today I will be presenting a question about stage design project for the upcoming Teachers' Day celebration. So, the question use measurement and geometry, and I use the scale drawing method. For group task, this question use iconic representation, but for individual, I decide to combine symbolic representation and iconic technical representation. Okay, now we move to the question. So basically, the question has give us several information. We can see the measurement in the image, and we obviously need to find the F, which is the front width. Okay, now we're going to move on to the introduction, which is real world context. Our school hall has a limited space of 4 meter width and 4 meter depth. We want a stage that fits inside this area while still providing comfortable movement for the performers, a 0.5 meter walkway on both sides for safety, a beautiful and modern design, enough space for 3 performers, stage height of 0.6 meter. To achieve this need, we decide to create a trapezium-shaped stage. The back width is fixed at 4 meters, while the front width, which is F, becomes a flexible design variable. This challenge brings mathematics to real life. We weren't just solving numbers, we were designing something that could actually be built. Okay, now I'm going to explain the solution. The solution that provided using a polyar form. Step 1, understand the problem. We can see we already have 2 measurement information and 1 unknown, which is F. We focus on 4 goals. First, to create a functional formula for the area. Second, to find a suitable range for value for F. 3, to select the best value of S such that they give the area greater equal than 5.4 meter square, practical and safe stage design and efficient material. The trapezium is isosceles, so both side length is equal. So step 2, we have 4 strategies. First, to use algebraic formulation to explore the constraint. Second, use table comparison, which is we will see a try and error attempt. 3, scale drawing, and 4, to justify the best choice. So, there are many other reasons that I use the iconic technique. Okay, after that, deriving to the area function. For trapezium area, at the top is the general formula. To create functional formula, we need to substitute the given information before we see in the general formula. So, here we get the final answer, which is AF equal to 1.5 F plus 6. This shows the area increase linearly as F increase and every positive F give the area bigger than 6 meters square. For slanted side length, we come out with 4 minus F divided with 2 because we know the back width is 4, but we have to provide 0.5 meter square walkway. And we use the Pythagoras as it shape a triangle, so we can easily calculate After that, feasible range of F. We have several conditions for the stage. First, the F must be positive number and it cannot exceed 4, which is the back width. It also must allow walkway and exceed 4.5 meters square. Therefore, the inequality form for F is F less than 0, less than equal to 4. Above a table of trial and error I mentioned to find the F value. So number 3 is the best value that give balance and ideal design. Okay, we move to the step 3. Step 3, carry out the plan. This is the calculation of trapezium area and slanted side that we will use to make the scale drawing. So, the scale 1 rational to 50, which is the 1 meter ratio to 2 cm. In the table, we can see the actual scale measurement. And the next slide, I provide the scale drawing and the plan with a proper measurement. From the scale drawing, we can see how the original measurement given, which is 4 meter, was converted to 8 cm on paper using a 1:50 scale, while the height of 3 meter becomes 6 cm and the chosen from width meter becomes 6 cm. This shows how the real dimensions are reduced proportionally so the whole plan fits neatly on the page without losing the correct ratio. By applying the scale consistently, every part of the figure remains in the right proportion, which make the drawing is faithful visual of the actual stage rather than just a sketch. Reasoning-wise, the scale drawing serves three purposes. First, it provides measurable evidence. We can read the slanted side directly in centimeter and convert it back to the meters, which verify the symbolic calculation. Second, it improves decision making. Seeing the trapezium at scale help judge whether the opening is comfortable, whether the shape look balanced, and whether the stage really fits within the 4 meter times 3 meter space while keeping the walkway. Third, it controls error communication. With a fixed scale, measurement can be taken to the nearest 0.05 centimeter. Lastly, we have material estimation. So for this part, we actually just calculate using trapezium formula. But this time, we substitute the 3, which is the answer for unknown. So we get 10.5 meters square, but we also have to remember logically, we have to add 10% allowance for cutting, and the final estimate we get is 11.6 meters square. For step 4, look back. From the calculation, the data matches the real measurement selected. The design make the constraint and both representation make the solution easy to see. For reflection, through the activity, I learned that the scale drawing are very useful in real life. They help us connect what we learn in math, like ratio and measurement, to something more practical such building or designing a space. When we convert the real measurement into smaller scale, it becomes easier to plan, draw, and communicate our ideas clearly. I also realized that using the scale drawing improved my understanding of accuracy because every centimeter on the paper represents a real measurement. If we make a small mistake on the drawing, it will affect the actual size later. So, precision is very important. Lastly, scale drawing may communicate much better. Instead of just explaining with words, we can show the exact plan visually. They help others understand quickly and reduce confusion. Overall, this style helped me think more carefully, apply mathematical reasoning, and work more confidently with measurement. I use scale drawing, which is iconic representation, to show accurate measurement and verify the stage can be practically constructed within the given space. I also use symbolic, which is algebra, to logically analyze the area and side length, ensuring the design is mathematically valid. By combining both representation, the reasoning became clearer, more reliable, and easier to communicate. In conclusion, the use of symbolic and iconic technical representation has guided me to identify the most efficient and practical design for the stage. The results show that when the front width equal to 3, the stage provides 10.5 meters square of usable space and requires around 11.6 meters square of materials, including wastage. The slanted side is also reasonable and can be measured accurately in both scale drawing and symbolic calculation. This confirms that the design valid both mathematically and visually. From this task, I realized that the mathematical reasoning is an important tool in solving real-life problems. It improves our understanding, supports clear communication, and allows us to justify our decision confidently. This experience has strengthened my problem-solving skill and made me appreciate how mathematics can truly help us design, build, and create something useful in daily life. That's all from me. Thank you.